Nuclear fission and fusion are two topics you'll need to know if you're doing the GCSE physics course. So if you're doing combined, you don't need to know too much, especially about fusion. Fission is part of nuclear power plants, so you need to know the basics of it for combined, but by and large, this is GCSE physics only. So, first of all, nuclear fission. Nuclear fission occurs when a larger nuclei splits into two smaller ones, often called daughter particles. Why does it split up? It's been made unstable. So, an isotope of a large nuclei, and in nuclear power plants and reactors, we typically use uranium or plutonium isotopes. When that large nuclei here absorbs a neutron, it becomes unstable and therefore undergoes decay to become more stable. So the neutron is kind of like the tipping point. It's like having, just too many objects to carry, everything falls to pieces. Any sorts of analogies like that work out there. And as you can see, the neutron hits the nuclei, is absorbed, and there are more neutrons produced after the event. And the two daughter particles are released. Now this releases energy, usually in the form of gamma rays, and everyone's heard of atomic bombs and atomic power plants. They're essentially the same thing in terms of reaction, but a nuclear power plant, the reaction rate is controlled, so the energy is released a lot more slowly. So the neutrons that are released afterwards, the three neutrons that come off after the nuclear fission event, they can go on to make what's called a chain reaction. So a chain reaction occurs when a single neutron hits a large nuclei. It will split into two daughter nuclei. At the same time, which usually power point effects release an awful lot of energy. This will also produce two or three neutrons after the fact. Now, those other neutrons can go on to hit other nuclei. So what we can end up in a chain reaction is the same thing happening over and over again. So these neutrons go on to strike large nuclei, end up with even more daughter particles and lots more energy. So we are essentially breaking nuclear bonds here that are holding nuclei together, and this is releasing energy. Now, if this happens over and over again in an uncontrolled fashion, you have an atomic bomb. But if you can control how quickly these neutrons are moving or what happens to them, then you can slow the reaction down. So on the inside of a nuclear reactor, we have these nuclear fuel rods, and sliding in and out of them, we have control rods, which can be moved in and out. These are usually made of carbon and can control how quickly the neutrons are moving, or just simply absorb them. So if they're removed, more neutrons are going to hit more fissile material here, more isotopes, and the rate of reaction increases. So if there's a reactor, if it's overheating, these control rods are moved down in between here to absorb more neutrons and decrease the rate of reaction. There's also water in the reactor under high pressure to control the speed of the neutrons as well. Now, surrounding this, there'll be a lot of heat given off. So that heat is used to heat up water, which would go off towards a turbine and a generator, which is how we get nuclear power. Now, nuclear fusion doesn't happen in nuclear power plants. It happens in the sun most commonly, and the sun is made up of about 75% hydrogen and about 25% helium, along with a sort of smattering of trace elements and heavy metals in there. And this is the fuel that's been used to create energy, this hydrogen, small nuclei. Now, nuclear fusion is when two small nuclei fuse together to form a single nucleus. So in this case here, we have one proton, which is a hydrogen nucleus, and when they are pushed together with enough force, they will stick together, and what we can end up making is helium. Now, in this case, This is a very simplified reaction because we've got 4 different particles here. We've added 2 neutrons, and we'll see why that is in a minute. But it's when the essential basics of fusion, we've got 2 small nuclei, and they're fused together to make a single nucleus. Now, protons naturally don't want to hang together because they're both similarly charged, and they will repel, just like 2 south poles of a magnet. So the positive charges repel. So they need an awful lot of kinetic energy. They need to be moving very quickly in order to force them together to form a hydrogen nuclei into a helium nuclei. So this is the slightly more complex version. Here we have an isotope of hydrogen called deuterium. It's got 1 neutron and 1 proton. And here we have another isotope of hydrogen called tritium, which has 2 neutrons and 1 proton. And when they are combined together, they form helium, and they leave a neutron along with an awful lot of energy, which is going to make its way towards the Earth, or in any direction from the Sun. And here we see 4 pictures. 2 are examples of nuclear fission, 2 are examples of nuclear fusion. The ones that are nuclear fission are the top 2. We have a nuclear test here. This is actually done in a place in the Pacific, a small island, which is a weird sort of star-shaped here. It's called Bikini Atoll. This is actually where the girls' swimwear, bikini, the name of that comes from. So there you go, a bit of history. And here we have a nuclear power plant where fission will be happening as well, albeit an awful lot more slowly. And then the bottom 2, we have nuclear fusion. We have the sun, obviously, which has given us our energy on Earth, by and large. And here we're trying to get fusion to work on Earth by using this sort of we're sending superheated gas around this chamber to slam into itself and get 2 protons to fuse to make a helium nuclei and give off lots of energy. Now, if we can get this to work, it will be carbon-free, very safe form of energy, but it seems to be one of those inventions that's always like 30 years away, so hopefully we'll manage to crack that soon, and we'll be able to reduce carbon emissions. Okay, hope you understood all that.